4:15. So I'm thrilled to introduce a colleague of mine here at Grimm, Jordan Cyr. Jordan is a recovering managed service provider, network administrator who got his start hacking as a hobby by modding video game consoles and playing with emulators. Turns out you can actually take weird hobbies like that and turn them into careers. So we're glad he's here at Grimm with us. Took Jordan way too long to realize this, but now he's a security researcher here at Grimm, working on some of the coolest cyber systems ever. And it's been about a year and a half since he joined the team and started his journey here, and he's thrilled with it. Says it's been amazing so far. So with that, Jordan, the floor is yours. Thank you.
Yeah, thank you, Jeff. So hey, everybody. Thank you for coming to my talk. My name is Jordan Cyr, as Jeff said, and today we're going to be diving into a topic that's daunting to most, but super cool once we get into it. And many of you have probably already heard of this. It's assembly language. So this is school assembly. This is a primer into reading and understanding assembly language and some hardware reverse engineering. So first off, a little bit about me. I went to college for a stupid major. I'm a business management major, but I've always had a love for computers and technology, and it's just really cool and really fun. So my first big boy IT jobs were systems administration and IT help desk, where I learned a hell of a lot. However, I like dealing with the tech more than with the people. And so my start into hacking was I discovered a glitch in a Super Nintendo game that had a bunch of weird behaviors and stuff, and wanted to learn how to do that on purpose, which led to me modding PlayStations and Wii's and like the GameCube and stuff. So that ultimately grew into the career that I have today. I'm an avid musician, as you can tell from the photo that's up on the screen. Shameless plug for my band, Chandler Reed and the Sticky Keys. So you can check us out on Spotify. I've been with Grimm for about a year and a half now as a junior cybersecurity researcher. I'm absolutely loving it. And I've got Freddy Krueger down here reminding you all to follow your dreams, because I never thought that I could take something like glitching or hacking video game systems and actually turn it into a career. So anybody can do this. Who's this talk for? This talk is for people who are brand new to assembly language. It's also for the seasoned hackers who are daunted by assembly, who are looking for maybe a refresher on their current understanding. This is also for the gluttons for punishment, or the masochistic, and I'm looking at the CTF people who are listening today. You guys are crazy. And this is also for the imposter. This is for people who think they have tricked everybody around them into thinking that they're real hackers, but they don't feel like they belong. But the truth of the matter is, we all feel that way. Everybody feels that way. That feeling never goes away. So ultimately, this talk is for whoever would like to learn. That's all it is. So what's the goal here? Hopefully after this talk, I'll be able to demystify some of what assembly is. So do we actually know what code does? Do we actually know what code does when we run it on a computer? And kind of get a feel for how we get from a high-level language, like C or C++, like high level, down to the lowest of lows, which is assembly language, which is what the CPU actually sees. So we're going to take this mess, like what you see on the screen here, and make sense of it. And then at the very tail end of this, just to kind of conclude, we'll be able to see this in action. We're going to take an assembly instruction and we're going to manipulate it, and we're going to see how it changes what the CPU actually does. So stick around for that. It's going to be really cool. First, we need to know what the heck even is a computer. So it's all just bits, right? It's all just bits. It's all ones and zeros. It's a glorified adding machine. And while this is true, it is oversimplifying things a lot. It's all ones and zeros, but so is my dating history before I met my wife. So, and she's also a 1 and a 0 because she's a 10. So anyway, I've said it's all just bits like a million times now. What does that actually mean? Well, what is a bit? Do we know what a 1 and a 0 actually is on a computer? What is a bit? Well, all a bit is it's just voltage. Bit is just electricity. Yeah, a good friend, manager, and mentor of mine, Timothy Brom, who also works at Grimm, once told me that there is no such thing as a digital machine. It is just an analog machine with rules. And that is to say that voltage is an analog signal. And all a computer does is it takes an analog signal like voltage. And if it's above a certain point, it says it's a 1. If it's below a certain point, it says it's a 0. So it's just an analog machine with rules. Now, those voltages, they travel along your computer and they go places, and that is the bit stream. The CPU, your processor, asks for those bits and interprets them, much like reading a book. The order that the bits enter the CPU determines how the CPU interprets them. So it's like it takes one chunk of bits at a time, depending on your architecture. And we'll talk about architectures in a little bit. It takes one chunk of bits at a time, interprets them, and does things. So one group of bits, depending on your architecture, it'll have different sizes. For one group of bits is one assembly instruction. It will execute that instruction and move on to the next one. And so that's basically the basis of assembly language. It is literally just the order of the bits going into the CPU, how the CPU interprets them, and then what the CPU does with that information and with that instruction. That's the bare minimum. That's the low level. We're going to go up from there. So I made a flow chart that maybe makes this a little bit easier to kind of visualize. So when we plug our computer into the wall, we get electricity. And then there's a whole bunch of magic transistor stuff that happens that your computer does to turn that into bits. And that magic transistor stuff is a whole nother talk that we're not going to go into today. But all you need to know is that it takes the signal from your wall and turns it into a signal that your computer can interpret. It changes it into ones and zeros, or binary, or bytes and bits. And then this little arrow branching off there, how the CPU interprets those bits, those are the assembly instructions. That is assembly language. Your CPU will then act on the hardware of your computer, or the RAM of your computer, using the instructions that it was just given by the bits that were flowed into it. Okay, are you with me so far? Okay. So what the heck is code then? How do we get from writing a C program, to our computer actually doing the stuff? So programming languages, all they are is just human readable instructions that we tell the computer to do. So high-level languages are tools that help humans create programs in compact packages to feed into the processor. And these are called binaries or executables. And all a binary or an executable is it's literally just a group of bytes or a group of bits, so that when it gets put into the CPU, it does what that group of bits tells it to do. Assembly code is what the CPU sees and what it actually does. So what we see are just bytes and bits and ones and zeros, and makes no sense to us, but what the CPU sees are instructions. And here's what I mean by that. So on the left here, if you can see the screen, which I would assume everybody can by now, otherwise somebody may have spoken up. On the left, this is just a very basic 9-line C code that takes two values and compares them against each other and spits out a string. If A is less than B, it prints out greater, or if it is greater, that it spits out not greater. So it just takes two values and interprets them. When we compile that package into a binary, we get something that looks like what's on the right. All the way to the right, we have these words, this push, move, sub, move. Those are the assembly instructions that the CPU is actually executing. And what's in the middle between the two are the bytes that are getting put into the CPU. So this is the actual binary ones and zeros that are being put into the CPU. CPU sees those and interprets them as the instructions that are going to be executed. Hey, buddy. All right, so everybody is always asking, what is assembly? Nobody asks, how is assembly? So how do we make sense of this? How do we read this and know what the heck is going on? So first, we need to talk about architectures. So what the heck is an architecture? Architectures provide context in which the processor interprets the bytes going into the CPU, and also certain properties of the system and behaviors. Architectures are very different across the board. And like the best way that I can kind of explain this is the same bytes or the same bits may have different meaning depending on what architecture sees them. That is to say, so what does the word Papa mean? And if somebody's in the Discord can answer that, that would be great. I don't see anybody answering. Well, Papa means father, right? It means dad. But what if you were in Mexico and you said Papa? What would that mean? Well, that means potato, right? It's the same word, the same information, the same data applied in two different contexts, one in English and one in Spanish, you know? So that's what I mean by architecture. The same bytes, the same bits mean different things depending on the architecture. So architectures will also determine the size of the general purpose registers on the processor. And if you don't know what a register is, I have good news for you because we are going to talk about that on the next slide. Because I didn't know what a register was when I got started doing this either, and I was thrown face first into it when I joined Grimm. And also, our architectures will determine the behavior behind some of the instructions as well. Ultimately, architectures provide context, they determine the register size, and they determine how the instructions are executed and the behavior is done. They're all a little different, but they all generally do the same things. All right, so what the hell is a register? A register is a very small, very fast, very expensive piece of RAM that is built right into the CPU. Because it is built right into the CPU can access it immediately. It doesn't need to go across any buses to access any information. So what a bus is it's just, it connects two pieces of your computer that allows data to flow between them. So because the registers are baked right into the CPU, it doesn't need to go over a bus. But say the CPU needed to access something in RAM, like a program that's been loaded up into RAM, it has to travel across a bus. There's a bottleneck there, so it slows it down. And with CPUs, we care a lot about speed, so we want those right next to it. Now, we can't have too many of them because they take up expensive and very precious die space on the chip when we're making them. So we can only have so many of them. And also, the architecture, like I said earlier, determines the size of the registers. So a 32-bit architecture will have 32-bit wide general purpose registers, and a 64-bit architecture will have 64-bit wide general purpose registers. And there are additional registers that also have separate purposes depending on the CPU and the architecture. You can have condition registers or state registers, floating point registers if the architecture is floating point compatible, vector registers, and there are more. But all you really need to know to understand what a register is it's just a very small, very fast, very expensive, they cost a lot of money to produce, piece of RAM that is baked right into the CPU. And assembly instructions will act on these. Okay. Here's a visualization on the next slide here. So from right to left, we have fast and expensive to slow to cheap. Okay. So on the far right, we got stupid fast. Okay. And then we have in the middle, we've got RAM or memory. And this is medium fast. So it's not as fast as a register, but it still needs to be pretty fast. So when we load a binary into a computer, the computer takes those bytes and it puts it into RAM. And then the CPU asks for those and then reads those bytes and then executes the instructions based on what it reads. So that needs to be pretty fast. It doesn't need to be as fast as the registers, but the access of that data needs to be pretty fast. And then when we're done with that program, it gets removed from memory and probably removed forever, but the actual binary file itself is stored on our hard drive or our solid state drive. And this is slow and cheap. Like you can get lots of, especially the platter drives, you can get a lot of storage on platter drives for relatively cheap now. Solid state drives are a little bit more expensive, but even those are coming down a whole heck of a lot. And this is, your hard drive is where your data that is permanent stays when there's no electricity going to the computer. That's called non-volatile storage. It is persistent without electricity. And these three parts of the computer are effectively all that assembly instructions deal with. These are the parts that we are interested in. So, oh my goodness, my cat hit my mouse, and so now I don't have the thing. Here we go. So how do we read this garbage once we actually get it? Okay. Most common, and like I said earlier, most assembly instructions are reading or writing to registers or RAM, and there's not a lot of different things that the instructions can do. Like 90% of assembly instructions are going to do math stuff. They're going to move things around. They're going to go places and execute stuff elsewhere. They're going to fetch information and bring it back, or they're going to compare. So all architectures, every single one of them roughly has these same behaviors of their instructions. They're all going to be a little different, but they're all roughly the same. So here are the common ones that we need to know about. Right? First up, we've got move. So what move does is it doesn't move things, actually. Move is copy stuff. Let's take stuff from here, copy it there. That's ultimately all it does. Now, very similarly to move, we have load and store, which is just load and store memory stuff. And this is mainly for specific architectures. They're called RISC architectures, but there are on other ones. There's exceptions to everything. This is similar to move, but specific to certain architectures. x86 or 64-bit Intel architectures, move is king. Move is for everything. But just know load and store also exists for other architectures. And then we've got add, subtract, multiply, divide, test, increment, decrement. Well, this is just math stuff. Just do math stuff to the values that are in registers or in RAM. Okay? Then we have and, or, XOR. This is just bitwise logic stuff. And if you don't know what bitwise is, that is okay. All you need to know is that they're logic operations that the computer does for comparisons and to manipulate data and read data and stuff like that. It's logic operations. That's really all they are. Then we have jump or branch, and this is just do stuff over there. Let's do stuff somewhere else. Okay? And very similar to that, we have jump 0, jump equal, jump not equal, and this is do stuff somewhere else, but only if conditions are met. These are conditional jumps. Okay, so those will get information, run a compare or a test on it, and if it meets the conditions, then it goes places. If it doesn't, just moves right to the next instruction. And then we have call. When we compile our code, our C code, we will have functions baked into them. And what call does is that's just do a specific set of stuff from somewhere else. That's go do that function. Do that function and bring me back the results. And in order to get back, we need to return. And that is go back to where you came from after doing the stuff. And this is like 80 to 90% of all instructions out there is just this bit. Oh, there's one more very important instruction that I forgot to mention, and that's don't do stuff. And that's called a NOP, N-O-P. And that's just don't do stuff. That's just move to the next instruction. That's all that one does. All right, so now let's take another look at that binary that I compiled earlier in the thing. So if we look at our instructions again, they start to make a bit more sense, right? So we see we've got a move instruction right at the top there. We have a subtraction instruction. We have a jump instruction down there, the JMP. Okay? Those are the instructions that the CPU sees when it sees these bytes. But how do we actually read these, right? Assembly instructions will have two parts. They will have the opcode name, the opcode name, or mnemonic, and then the operands. Now, the name is just the name of the operand. In this case, this is a PowerPC instruction, and it is an addition instruction. And the operands are just the parts of the computer, the registers or the RAM, that we care about when we are reading this instruction. Okay. Operands can be three different types. They can be registers. It could be memory dereferences, which is values that are stored in RAM at a particular location. Those are normally denoted with brackets or with greater than or less than signs. And then we have immediates, which immediates are just numbers that are hard-coded into the instruction themselves. So that is a part of the bytes that are put inside the CPU or that are in the bit stream. A part of them, say, has the value 2 in it. And when the CPU reads that instruction, it's going to interpret that part of the instruction as the value 2. That's all an immediate is. It's hard-coded, baked into the instruction value. Now, after you execute an instruction, what do you do with the result? Well, you have a source operand and then destination operands. And these are all architecture dependent. And the position of where the operand is in the instruction determines whether or not it is a source or a destination. In this particular instruction, we have add register 1, register 2, register 3 in that order. PowerPC, the destination register is always the first operand listed. So this instruction is telling us to take register 2, the value that's inside register 2, add it to the value inside register 3, and store it inside register 1. Okay, let's take a look at another example, this time with a memory dereference. And we use x86 this time. So this is a subtraction instruction, and it has a memory dereference on it, right? Memory can also be a destination. x86 is the same as PowerPC as far as the destination goes. It will be the first operand. In this case, we are taking the value stored in the location of the value of ECX plus 19FC hex. And that's the location of the in RAM that we are interested in. And then we are subtracting the value inside EAX from that and storing it back inside that value, or back inside that location. And if it doesn't make sense right now, it's okay, because we're actually going to use this instruction in a demo right now, okay? This is demo man. If you get the pun, great. So this exact instruction is actually the instruction in the PC Steam release version of Chrono Trigger that you use to buy things from the store. So here, this is me playing the game. We talked to this kid, and we're going to go to the store, and I've already done the hard work of locating the memory value or the memory location where our gold is stored. So I've already given us some extra gold to play around with. And I've already located the instruction in the binary that we're going to be using. So you go to a store, what normally happens is you will buy something, and you can see my money is going down as I buy these padded vests. You know, 300 at a time. Buy a bronze helmet, goes down 200. Well, here's that instruction. If it's a little hard to see, it's okay. It's on the previous slide. It's subtract ECX 19FC EAX. Okay, there's the instruction. Now we're going to change this instruction, and we're going to see how that affects the behavior. So let's change this to an addition instruction. All right, so now what's going to happen when I buy something? Okay, so when I buy something, they're going to pay us to take it from them. So let's buy a padded vest. It's going to go up by 600. They're paying us to take all their stock now. And because the instruction's baked into the binary, you can use it wherever. So let's go to Melchior over here. Oh, he's got a silver sword for 4,000 gold. Oh, he's going to pay us to take those from him. All right. So, and that's really the basis. And you can see that value in memory is unchanged, you know, or well, it's it's persistent across. So, all right. Next slide. How we doing? How are we feeling? Assembly language is difficult. It's a lot to take in all at once, and this is just a bite-sized nugget of kind of like what to expect and just a little bit to understand. But it is okay. The more you practice, the easier it gets. And the basics is literally just assembly instructions are just bytes that are interpreted by the CPU to do stuff. If you take anything away from this this talk, it's just that. Assembly is just bytes that the CPU interprets as instructions to do stuff. Thank you so much for listening to this. And now I've got went a little over. I've got like 12 minutes for questions. So if anybody has anything for me, I'm looking at the Discord here, and is there a chat here? But Jeff or whoever's here, you can come back in now.
Yeah.
Oh, Joyo. All right, cool. We got Sean and Joyo.
Yeah. If anyone has any questions, please feel free to put it down in the Discord chat for track 2. I will ask them on your behalf. Thanks, Jordan. That was real good. I love a good intro to assembly. I definitely missed out on those classes when I was going to college. I had to learn those basically on my own.
The first project that I was put on at Grimm was, here, make a PowerPC emulator. And if you're going to start with any language to learn assembly, I do not recommend PowerPC.
but it's so fixed length. It's doing all the hard work for you.
It is and it's not. It is until it's not.
It is until it's not. That's true.
So, but that's actually a big thanks to Matt Carpenter and Aaron Cornelius, because they actually kind of took me under their wing, and they kind of helped inspire me to make this talk, because assembly is very daunting. It's very, people hear it and like their butthole clenches, you know. So, but this is hopefully taking it to a point where it's like a little bit easier to consume. And so that was the goal behind this. And so if there are any questions, I would love to hear them.
So I haven't seen any in Discord, but I did have a question. So what kind of applications do you see a lot for assembly that the audience may not be aware of? Like where are you using assembly the most?
Oh, we use it on the sci-fi team for reverse engineering. So if we get like a binary off of, say, like the firmware of a car, we can load that up into a debugger and then step through the firmware itself and find exploits that way. Hooking things up to a debugger and being able to step through it one by one instruction at a time, really helps to kind of visualize what the computer itself is doing. And Tom is saying, Tom, my coworker and good friend, has been digging through binaries, or ARM binaries, for a while now. So he knows more about ARM than I do by a lot. But I would say it's most useful from a reverse engineering standpoint. On a day-to-day, for me, I use it to hack video games. Like you just saw. Take an instruction and change it to what I want it to do. I want people to pay me to buy stuff from the stores.
Yeah, so it's notable to mention that like writing assembly and reading assembly are two very different things. Like it's the same syntax. In fact, you know, in most reverse engineering tools, you can pick what syntax you're using if it's Intel or AT&T. But when you're reading assembly, it's never really, the intention is never really obvious, right? Like compilers do wild things, especially with anything that's using vtables. So putting what the instructions you're seeing in context becomes a lot more important than when you're writing it, in which you can basically label, you can write C and then see what assembly gets created with that. But even then, the compiler is going to be doing some interesting tricks. But you can also write assembly like you would write C. Go ahead. Go ahead.
So when I compiled that little C code for the presentation, there was a lot of stuff that I had to cut out that are just like library loads and stuff like that that we didn't really need to worry about. Just the meat of the main function is what we cared about. Secure in Style asks, what advantages are there, if any, to programming or developing in assembly as opposed to higher level languages? And so I forgot to mention this in the presentation, but I meant to. We used to have to write assembly language by hand on punch cards. So the first computer programs were actually literally punch cards that were fed into machines that would interpret them. We. And so, but which is great for small programs. But if you've got a program that's even 1 megabyte large, that is a stack of punch cards that is like going to be the size of my room here. And so we use high-level languages that we've developed in order to avoid that. So we don't have to do that, which is great. You know, you can still do it. You can still go into your compiler on your computer and feed it bytes and still spit out a binary that is compiled or that you wrote by hand. But it's much easier to just use code or high-level languages now.
I mean, even 10 years ago, 5 years ago, assembly, writing natively in assembly is a preferred method for speed, right? If you've got like a real transaction, like an ATM or a bank transaction that has to happen right now, it would still be done in assembler. But with the speed of computers these days and networking, you don't see a need for it unless you're doing really small, simple things like, I don't know, an embedded ECU in a car that handles braking, right?
Yeah, well, the other side of that is you need to do something small. So there's speed, but then there's also size. When you're doing vulnerability research and you want to, create an exploit to demonstrate the vulnerability you've discovered, you may not have all that much space to really work with. You've got maybe enough room to allocate more memory if you're lucky.
Or you set up a trampoline if you've got access to a debugger. But if you got access to a debugger, you're effectively done anyway.
Yeah. Well, you want to use the debugger to write your exploit. That's how you know what even is going on. You're not going to get nice errors from what you're doing.
Sure. Mm-hmm. Well, that's it for me. Unless anybody else has anything for me.
I have one that did not get answered. Hang on. So we had why is assembly, who is assembly, and how is Oh, and when is assembly was my favorite. When
is assembly? It started in about 1940, I think. Before that, I don't know. Whenever they were making room-sized computers is when assembly started, I guess. But who is assembly? Well, that's all of us. Why is assembly? Well, why not?
It might be worth mentioning that assembly isn't even really the machine language. Like it is still an abstraction for human readable eyes. The actual machine code really is just ones and zeros, and it's presented in a format for the processor.
It's like disassembled assembly language is like, I think of it as like human readable computer bytes.
Right.
And I'll put human readable in quotes because it still makes no sense if you're just staring at it. You have to step through it and see what it's doing to get the full context and to get the full understanding of what the program is actually doing. and I still suck at it too. Like it takes a lot of practice to get through it and to actually understand what the computer is doing and why it's doing it.
Yeah.
Awesome.
Another thing you might want to keep in mind when learning assembly is that if you're trying to execute this assembly, you should probably know what your calling convention is, depending on your operating environment. So if you're productizing an exploit, you need to know whatever processor you're exploiting, what the calling convention is, especially if you plan on doing any kind of syscalls.
I didn't want to get into calling conventions on an intro course.
Yeah, no. It's definitely not intro. But I do like mentioning it, so it's not the first time you hear it.
So when you hear it, just know that calling conventions are a thing. Also, there's the I forgot to mention, whatever architecture you are dealing with, there are books upon books of documentation for most all of them that will lay out what the behaviors are and what the instructions themselves are doing individually. And so if you are reverse engineering a PowerPC binary or an Intel binary, it would behoove you to read through the documentation about that architecture in order to get the full context.
Yeah,
And they're free. They're free to the public. Too, so.
Yeah, that's the nice thing about Ghidra, the NSA reverse engineering tools. They include most of the processor architecture manuals, specifications in the zip. And if I'm not mistaken, you can just right-click on an instruction when you see it in whatever it is that you are exploring, and it will go to that page in the documentation, which is really helpful.
Your results may vary.
Right. It's not foolproof. But I believe that is the intent, and I suspect it may have been broken in some ways when it was published.
Mm-hmm.
So are there any like simulated event environments or emulators perhaps that you could use?
Absolutely. You could use to practice. A very popular one that I used when I was hired into Grimm is called Microcorruption. It's microcorruption.com. And it's an MSP 430 emulated debugger and disassembler that teaches you how to step through programs, and you're virtually popping a lock. And then it's just like a regular GDB debugger interface. But you got your assembly language right there. You've got the disassembly, and then you have the memory space and the bytes right down there. It's very, very easy to get started, and there's lots of people that have done this, and so you can look up write-ups on how to do some of the challenges if you are stuck. So I've done a few of them. Many people on the sci-fi team here have completed all of them, but I'm not a masochist. But yeah, it's a lot of fun. That was my first soiree into disassembly, and I don't even know what I was dealing with.
All right. All right. Well, any other questions before we lose Jordan?
We Gucci? So, thank you so much, everybody.
Jordan.
Yeah, continue the rest of the con.